Hi, everyone. Welcome back. We're going to study Chapter 3 of Chemistry 105 about climate change, or now we call it global climate change. In this chapter, we're also focusing on the radiation from the sun, but meaning on IR radiations. And also we're going to talk about what is the topic of climate change means and what are the causes, okay, and what's something we can do or to prevent or to improve. So here are some questions for this chapter. Okay, we want to talk about what are the sources of carbon on Earth, because a lot of times when we talk about global climate change, we connect the topic with carbon release, okay, carbon amount. So we also want to ask, how does carbon move between reservoirs and how do scientists measure the amount of carbons? And what are greenhouse gases and what are their positive and negative effects? And what are the global consequences of climate change is what would cause, what climate change would cause? And also, how do our current climate trends is different from the past? How do we know we have a climate change? And also, what our daily lives, what our actions can affect the global environment. So these are some questions we want to ask about this topic relating the amount of carbon released and also the change of climate and also the chemistry involved. So first, let's talk about the topic, global climate change. Okay, global climate change. The global climate change, sometimes people call it global warming, is the observed century scale rise in the average temperature of Earth due to human activities, primarily due to burning of carbon containing fossil fuels, and also the related effects of the temperature rise of the Earth climate system. Now, climate warming, because the change is basically moving a rise of temperature. So global warming and global climate change, these two terms are actually often used interchangeably, okay, But climate change, okay, climate change normally refers to both human and natural produced warming, okay, produced warming. Global warming mostly, if I'm understanding this correctly, are talking about human activity, but global climate change, this term mostly refers to both human and natural produced warming and the effects of that. Okay, so this picture from NASA's Institute of Space Studies shows the global surface temperature, okay, from 1951 to 1980, the average temperature, global surface, the average temperatures. And you can see that with the year, the global surface relative to 1951 to 1980, the average temperature, you can see that the temperature, average temperature, surface temperature of the Earth is actually increasing, okay, increasing. The year of 2020, tying with the year of 2016 for being the warmest on record. Okay, you can see compared to the average temperature around the 1980s, the temperature rised up approximately 1 degree. Okay, sometimes people will think, oh, 1 degree isn't that much, but when we talk about the global average temperature, 1 degree is actually a significant rise for the average temperature. Okay, 1 degree above the 1951 to 1980, the baseline. Now, in order to understand that, okay, what caused it? What are the potential causes for the global surface temperature rise? We have to know what causes or maintain the temperature of the Earth and what causes the temperature to rise. There are two facts about this topic. First is we do need our climate or our planet to be warm in order to survive. And another topic is, but we're actually keeping our extra warm so that the average temperature is increasing. So first, let's take a look. Okay, let's take a look. What radiation from the sun, what part of the radiation from the sun keeps us warm? And as you recall this picture from chapter 2, you will see that, besides the visible light and the UV light part, 53% of the total energy emitted from the sun is radiated to the earth as infrared, IR. Okay, and we mentioned that in chapter 2, IR, this portion is the main source for heating our planet. Okay, heating our planet. And this picture shows you for all the radiations, okay, if you count as 100%, 46% of the sun's radiation is actually absorbed by the earth. Here, 46. Okay, some are reflected from the atmosphere, some are absorbed by the atmosphere, but some are reflected from the surface, etc. But 46% is absorbed by this big rock of Earth. And during nighttime, okay, during the radiation, 46% will be remitted, in the form of IR, okay, in the form of back to the universe, back to the outer space. But out of these 46%, 36 remitted here, 37% remitted will be absorbed by our atmosphere. Okay, so that means for the 46% of energy that absorbed during the day by the earth, by the big earth, during the night, certainly 36% will be remitted. Okay, will be remitted, sorry. Second, let me figure out what's going on for the sharing. Sorry, let's continue. Okay, like we mentioned before, 46% of the radiation from the sun is absorbed by the earth. And the earth will be remit the energy back to the universe as IR radiation. And 37% out of the 46%, IR radiation is absorbed by the atmosphere. And because of that percentage, because the major percentage, 37 out of 46, you can see that, out of 46, it's around 80%. Okay, because of that major percentage is trapped by the atmosphere. That is why our planet Earth can be maintained at an average temperature of 15 degrees Celsius. Okay, at a warm temperature, habitable temperature. And that trapping heat in the form of IR by the atmosphere is called a greenhouse effect. Okay, and without this natural balance, you can see that the average temperature of the Earth will be minus 18 degrees Celsius, which is way below freezing point. Minus 18 will be the temperature of a freezer. Okay, minus 20, minus 18. And will be inhabitable. So our atmosphere has a greenhouse effect that traps the heat in the form of IR. Okay, we know, okay, I know the atmosphere is composed of what? Composed of gas, air. So there are some components in the air that serve as heat trapping gases. And we call those gases greenhouse gases. Okay, greenhouse gases. What are greenhouse gases? Greenhouse gases are gases capable of absorbing and trapping infrared radiation, thereby warming the atmosphere. The main greenhouse gases are two. The first one is water vapor. Okay, moisture in the water vapor, causes about 36 to 70% of greenhouse effect. And the second most important one is carbon dioxide, which causes 9 to 26%. And the other ones include methane and ozone. Okay, these are minor contributors of greenhouse effect. But the most important two are water and carbon dioxide. Okay, and again, the presence of these gases, the greenhouse gases, is essential for keeping our climate warm. Now, water vapor, the most important greenhouse gas, the concentration in the atmosphere doesn't change. They change with climate, but doesn't change, fluctuate much. But if you look at this chart, you find out the greenhouse gas carbon dioxide concentration. This chart is ranging from 1958 to 2020. Actually increased significantly from 320 ppm to almost 420 ppm. And this year, 2022, it has a peak value at 418.81 ppm in March of 2022. Okay, this is the highest level of carbon dioxide. So carbon dioxide, the greenhouse gas concentration is increasing. So we assume this is the initial causes for temperature change. And of course, we're measuring the change of carbon dioxide concentration. If you notice that the carbon dioxide concentration actually fluctuate within a year. Okay, we call that seasonal fluctuation. Okay, seasonal fluctuation with around like a during the spring, this the highest and start to drop and then rise again and then drop. You can see there's a seasonal fluctuation within a year. Okay, the red dashed line represents the monthly mean values. Okay, you can read relative amount called Keeling's curve, why there is a seasonal fluctuation about the carbon dioxide concentration. And these are the recent data, okay, from 1952 to recent. And if we really want to know historical data of carbon dioxide, we have our own way. Scientists can actually get the carbon dioxide concentration from a long time ago, from a vertical timeline by digging ice cores from glaciers. Because in ice cores, there will be air bubbles trapped inside the ice core. If the air bubble trapped inside, then the concentration of the gases in the cores, the bubbles will be kind of like a fixed frozen, and which represent the age, which represent the time when it was trapped. So basically, the deeper you dig, if you know the age of the core or the age of the layer, you know when the air was trapped, and you know the concentration of the gas at that time point. The deeper you drill, of course, further back in time. So with that technology, we can actually know the carbon dioxide concentration all the way dated to what? Here, this picture shows you 800,000 years. And you can see that this Vostok ice core shows back to 400,000 years, and while other cores go back even further. And we did notice that, even though the carbon dioxide concentration also fluctuate over the long time period, but the highest previous concentration is around 300 ppm. And nowadays, you can see that the average of 2018 is at least 100 ppm higher than any time in the last million years. And if you plot the concentration of carbon dioxide and the global temperature together, you can find some correlation over the past 400,000 years. You can see that the blue line is the carbon dioxide concentration, the red line is temperature, global temperature. So you can see that higher carbon dioxide concentration normally correlates with higher temperature, lower means lower temperature. Of course, the blue line nowadays, the temperature, the carbon dioxide is highest around 400. So we're actually at higher temperature peak of the cycle, of that cycle. And by the way, here, these parts with very low temperature are called ice ages. Okay, you guys have heard of ice age. These are ice ages when temperatures are low in millions, hundreds of years ago. And here, is a link with some data for historic climate trends. Take a look. So basically means what? Methane means we're actually putting more carbon dioxide than before. At least we know that. Okay, we know carbon dioxide concentration is higher than any time before, 100 ppm higher. And so next question we want to know, hey, how do we put more? And what is there any like a math between we put some carbon dioxide into the atmosphere or something we remove from? And this is shown here, called a global carbon cycle. Okay, the global carbon cycle shows you not only the atmospheric carbon dioxide concentration, how much we put in, how much we put out. We actually shows you the whole balance. And we also show the reservoir of carbon dioxide, of carbon. You can see that we have something in the rock, in the fossil fuel, in the rocks, and also in the deep ocean. Deep ocean is actually a big reservoir of, the ocean is a deep reservoir of carbon dioxide. But if you can look at this red lines, you can see that some arrows pointing into the atmosphere means what? Means we're putting carbon dioxide into the atmosphere, and some arrows are going back, like photosynthesis, like reforestation, and also dissolving the ocean water. We're taking carbon dioxide away from the atmosphere. So if you do a math, like adding the ones we put in and adding the ones we remove, you will find out that we are actually putting in, I did some math here in my notes, you can take a look. In is the one we put in is 157.5 gigaton per year. And the one we remove is 153.5 gigaton per year. This tells me us what? We're putting, of course, apparently more carbon in to the atmosphere than the ability or than our. Okay, those are the carbon data, shows you what. And of course, we're putting in there some human activities, and these are some human activities that contribute to carbon emission, carbon dioxide emission. Most significant contribution is what? Is burning of fossil fuel. Okay, burning of carbon-containing fuels, fossil fuels. Okay, burning fuels for electricity, transportation, and heating are major contribution to the carbon dioxide emission. And of course, every second rainforest is cutting down or burned to cover to, like every second how much forests are reporting that how they're cutting down. Also contribute that because you got less forest to remove carbon dioxide through photosynthesis. And here's the pie chart, shows you the percentage of contribution for increasing the carbon emission. And here this picture shows you top CO2 emitting countries from 1950 to 2020. You can see that those large countries, United States, China, Russia, Germany, Europe, countries, they are the main countries emitting carbon dioxide, the greenhouse gas in the atmosphere. Okay, again, we're bringing out the facts, to talk about, to help you understand, and also eventually, I hope you make your own decision about this debating topic. Okay, it is still a debating topic. And here, okay, before we study more chemistry, I want to show you a few potential consequences of climate change. Okay, one big consequence is if our climate gets warmer. Okay, what's warmer? The sea ice of Arctic is actually what decreased because you're going to melt ice, and the melt ice, what you're going to have rising sea level. Okay, rising sea level. So that means some cities, if the sea level is going to change, some cities will be underwater. Okay, sea level change, some cities are going to be underwater. Okay, you can see that this map shows you the sea level change. The green one is actually increase the level. And of course, brown, the orange one is decreasing. You can see most of the part is sea level is increasing. Okay, sea level is increasing. The other impacts, okay, other impacts of climate change, including more extreme weather, storm, drought, flooding, and also the change of ocean chemistry, the loss of biodiversity because of the ecosystem is changed. That means changing the range of habitats or extinction of some biospecies, and also vulnerability, increasing of vulnerability of freshwater resources, and also human health. These are some other consequences. Okay, here it shows you a very famous picture. Because of global climate change, the melt of sea ice, okay, 2/3 of polar bears would disappear by 2050. And also here, another consequence of global climate change is because of the increase of carbon dioxide in the atmosphere, carbon dioxide will dissolve more in the ocean water, will cause the pH of the water to further decrease. We call that ocean acidification. Okay, you can see that pH level of ocean water is going to decrease. Okay, year by year, here's the pH level. And the pH decrease will cause the dissolve a lot of seashells or sea creatures, coral, to start to dissolve. Okay, start to dissolve. So here again, I'm bringing out the fact, showing you the why we have the topic of global climate change and what are the potential causes, and also bring out the facts that carbon dioxide level is increasing. And during the past 800,000 years, the carbon dioxide rise and down correlates well with the rise of down of temperature. And right now we have a higher temperature range. But again, this is a debating topic. I hope you know the facts and do your own research, do your own study, and do your own discussions, and find out your decision and your thoughts on these. But after that, let's take a look some chemistry. The most important one now is we want to know, hey, why water and carbon dioxide, these two main greenhouse gases, can trap heat, can help us to absorb IR radiation from the earth, can keep us warm. Okay, in order to study that, we need to learn a very important topic. Okay, that is the geometry of molecules or the shape of molecules. Okay, shape of molecules. The reason is that IR absorption by these molecules will cause the vibration, such as bending and stretching of these molecules. So in order to know how they bend, how they stretch, we first need to know what? Know the geometry, what they look like. And also why carbon dioxide and water, they can vibrate, they can absorb IR, but other molecules like the main component of the air, nitrogen and oxygen, these diatomic molecules, why they don't absorb heat or absorb IR. So these are all can be explained after we know the geometry of the molecule. Okay, now in order to know the geometry of a molecule, especially a gas molecule, the first and foremost important thing is something we learned from chapter 2. That is correctly draw a Lewis structure. Okay, Lewis structure. Only you have a correct Lewis structure on the two-dimensional paper, we can from there to predict a three-dimensional geometry of a molecule. So first, you still need to review chapter 2 and be able to determine the Lewis structure of the molecule. Okay, again, I put these 3 steps or maybe 4 steps and also molecules for you to practice with. Okay, there's the molecule in the box, in the box, you can practice them with them and feel free to ask questions. Okay, these are steps. Determine the sum of total number of valence electrons, draw the skeletal, okay, if you still recall the steps, and connect the central with the surrounding with a single bond, and then satisfy the octet of the surrounding first, and then put the remaining on the central and check whether everybody satisfy the octet. If not, you need to try double and single, double, and triple bonds. So again, please practice so that you can very comfortably draw a correct Lewis structure. Now, after we have a Lewis structure on a two-dimensional paper, okay, that Lewis structure shows how the atoms are bonded together, how they are connected together. Okay, how they're connected together. They are connected through bonds, but those bonds can be shown very nicely in a Lewis structure. However, because it's two-dimensional, we cannot tell the geometry of the shape or three-dimensional geometry of the molecule. So we need to know how to do that, because the geometry not only can tell how they're bonded together, but also the geometry can tell us or help us to predict the physical and chemical property of some substances. So how do we know the geometry? From the Lewis structure, we can count two things. We can locate two things. One is we can locate the valence electrons are in different groups. Remember, valence electrons are around the central atom. If we look at the central atom, we can tell how many groups of electrons are on the central atom. Okay, how many groups of electrons are in the central atom? And this group of electrons, again, we're talking about the central atom, because when you determine a geometry of something, you look at the central atom and how the central atom is interacting with the surroundings, so you know what the geometry. Just like a flower, right? You know the center of the flower, and then you figure out how the petals are attached to the center. You know the geometry of the overall flower. The same idea. Here, when we talk about the molecule, we look at the Lewis structure, and we look at the center of the Lewis structure so that we know how many groups of electrons are on the central atom. Okay, how many groups of valence electron on the central atom? And why we care about electrons? Because the electrons are in groups, and the electron groups will what? Will repel each other. The electrons are negatively charged. So there's repulsion between the negative charged electron groups. And that repulsion will help us to determine the geometry, because electrons will adopt, the molecule will adopt a geometry that what? Minimize the geometry. Okay, minimize the geometry, minimize the repulsion. Okay, that molecule will adopt a geometry so that the electron groups will have minimum repulsion. Okay, for example, I put the three cases here, A, B, and C. You can see that what I mean. Okay, first, if let's say this is the central atom. If the central atom has two groups of electrons, okay, just like here, two lone pairs, but we assume there are two groups of electrons. And two groups of electrons, if they repulse each other, then the maximum distance, biggest separation of these two groups will be what? Will be adopt this left and right geometry. We call linear geometry. Because only when they're 180-degree angle, like a left and right, top and bottom, front and back, whatever you call it, geometry, these two groups of electrons have minimum repulsion because they're further away from each other. The same, when you have three groups, these three groups will adopt a geometry called trigonal planar. And when you have four groups, these four groups will adopt a geometry called tetrahedral. So this theory, we call it VSEPR, or valence shell electron pair repulsion theory. Basically, we care is how many electron groups are around the central atom. And based on these electron groups will adopt a geometry so that they can be maximally separated. So the repulsion is what? Repulsion is small, the smallest. Okay, again, it's some abstract. Let's take a look at a few examples. Okay, so that you can get the idea. The first example, okay, the first example is carbon dioxide. Okay, carbon dioxide. Again, first, guys, you need to know how to draw a correct Lewis structure. That's the most important part of this chapter. Okay, before you can tell the geometry. This is the Lewis structure of carbon dioxide. Apparently, the carbon is the central atom. Okay, carbon is the central atom. And you can see that on the central atom carbon, we have two double bonds. So each double bond is a group of electrons because those electrons, 4 electrons are in the same group in that particular group here. And the other double bond is another group. So this central atom of carbon has 2 groups of electrons on it, even though they're both double bond, but there's 2 groups. And those 2 groups of electrons will repulse each other. So the maximum separation is what? Is when these 2 groups are 180 degrees. We call that the bond angle. And because of that maximum separation, the geometry of the molecule carbon dioxide is called linear. Why? Because 180 is called linear. Okay, it's called linear. And I think with the molecule, you can see better. And another example, SO3. Okay, SO3. This is the Lewis structure of SO3. You can see on the sulfur, there are 3 electron groups. Okay, one is a double bond, a single bond, another one is a single bond, and another one is a double bond. But again, no matter they're double or single bond, the electron within that bond is in a group. So on sulfur, the central atom sulfur, there are 3 electron groups. When you have 3 electron groups, these groups can be maximally separated when the bond angle is 120. Okay, when the bond angle is 120. Let me grab some pins to show you. So this is 3 electron groups. Okay, the bond angle is 120 means what? Means these 3 bonds are in the same plane, like a triangle. Okay, they make a triangle like a triangle, same plane. See that? And the bond angle here is 120, 120, 120. And we call this geometry trigonal planar geometry. Why? Because the molecule is in the plane. The central sulfur and the oxygens, okay, the oxygens are in the same plane. Okay, if you wait for me, I'll grab some model to show you better. Okay, let me pause the recording and I'll grab some model to show you. Hey guys, so let's take a look. This is what a carbon dioxide molecule looks like. You see that? 2 double bonds, 2 groups. So the geometry is linear, like a line. See that? This is the geometry of the carbon dioxide. Okay, the geometry of this sulfur trioxide, I use these 3 pins. It's easier because I don't have that model. But these 3 lines are in the same plane. Okay, 3 lines in the same plane. So we call that trigonal pyramidal. You can see that all 3 bonds are on the same plane, and the bond angle is 120. Okay, bond angle is 120. Now, if you look at another molecule, ozone. Okay, if you look at another molecule is ozone. Here is the Lewis structure of ozone. Okay, Lewis structure ozone. What is different between this molecule and the previous one is this sulfur trioxide has 3 groups. And ozone also has 3 groups because the central oxygen, okay, let me erase that. The central oxygen has 1 lone pair, 1 single bond, and a double bond. So on the central oxygen, it still has 3 different groups. Okay, 3 different groups. 1 lone pair, 1 single bond, 1 double bond. So three groups, we know the geometry of these three groups should be what? Should be trigonal planar. However, because one of these three groups, single bond, double bond, lone pair, is a pair of electrons. That means there's nothing on it. There's no bonded atom on it. This is just a pair of electrons. So the geometry of the molecule is actually derived from the trigonal planar. What does it look like? We call this a bent geometry. Okay, a bent geometry. The pairs, the electron group pairs, lone pair, single bond, double bond, is still trigonal planar arranged. But the molecule describing owning the atoms, this is the lone pair of electron, a pair of electron here. Okay, this is the electron, a pair of electron here. This pair of electron group doesn't have anything attached to. This is just a pair of electron over here. So the geometry of the ozone molecule is owning these here, O, O, and O. So oxygen, oxygen, and oxygen. So the geometry is what? Is bent. Okay, we call it bent geometry. You can see this is the model of ozone. Okay, model of ozone. And if you want to build a model of ozone very quickly, we can show you the model of ozone. Look like this. Okay, the model of ozone look like this. Okay, the model of ozone look like this. 3 oxygens. Yeah. 3 oxygens. See that? A single bond and double bond is shorter, so we would kind of put it to a different, but the geometry is bent. Okay, we know this is one resonance structure, the real structure, these bond ends should be the same. But the bond angle, because it was from trigonal planar, remember there's a lone pair, so the bond angle is still close to 120. Okay, here it shows 117. Okay, we just assume it's 120. Okay, that deviation from 120 is beyond the topic of this class. We don't discuss that. You can assume it's 120, the bond angle. Okay, that's for 3 electron groups. You can see these two are different. For sulfur trioxide, 3 electron groups are all the same. They have all 3 atoms there. So it's trigonal planar geometry. This is what trigonal planar looks like. But for ozone, you also got 3 groups. But one of the group here is what? Electron, nothing on it. So the geometry of the molecule is bent. Okay, it's bent. Now, what if we have 4 electron groups? If you have 4 electron groups, such as methane, CH4, okay, this is the Lewis structure. You can see around the central atom carbon, there are 4 single bonds. 4 single bonds means 4 electron groups. And these 4 electron groups needs to repulse each other. The maximum separation is a geometry called tetrahedral. Okay, this is what tetrahedral look like. You can see the center one is the carbon. Okay, the center one is the carbon. And 4 hydrogen around it is a 3-dimensional shape. Okay, 3-dimensional shape. Okay. And by that, these 2 bonds are maximally separated. Okay, you can see the maximum separated. And the bond angle between any CH-CH bond here, the bond angle between any CH-CH bond is 109.5. That's the bond angle for tetrahedral shaped molecule, 109.5. Okay, again, this is the geometry of tetrahedral. Now let's take a look at another molecule, ammonia. Okay, NH3, ammonia. Again, guys, you can see there, I get rid of the step of drawing the Lewis structures. That's why you need to know first how to draw a correct Lewis structure. I cannot emphasize this enough. Okay, this is the Lewis structure. Okay, this is the Lewis structure of ammonia. And if you can practice now, you can see that on the central atom, okay, on the central atom nitrogen, there are how many groups? 4. 3 of them are single bonds, and 1 of them is a what? Is a pair of electrons. So 4 electron groups. Now, if we have 4 electron groups, we know what? We know the geometry of these 4 groups is tetrahedral. Okay, these 4 groups is tetrahedral. However, you notice that in ammonia on the nitrogen, one of the group is what? Is the electron. This is a pair of electron. There's no atoms on it. So the real geometry of the molecule is like this. Okay, I'm going to use the real model. The real geometry of the molecule is like this. We call that trachinopyramidal geometry. Okay, the nitrogen is actually slightly above the plane of the 3 hydrogen. See that? Okay, slightly above the plane of these 3 hydrogen. We call that trachinopyramidal geometry. Okay, trachinopyramidal geometry. Why is that? Because this geometry came from what? Came from tetrahedral. But the one of the group, electron group, is what? It's lone pair electrons. So there's no bonded atom here. So that's why we derived to get a shape of what? Trachinopyramidal. Okay, trachinopyramidal. Next, let's try look at the water molecule. Okay. We know water molecule, Lewis structure is this. On the central atom, oxygen. Okay, on the central atom of oxygen, again, I think you can count now, we have 2 single bond, and we have 2 what? Lone pairs. So totally we have what? We have 4 electron groups. If we have 4 electron groups, again, guys, the geometry of the 4 groups should be tetrahedral. Okay, 4 electron groups should be tetrahedral. However, 2 of those are lone pairs. There are no electrons, no atoms in there. All you have is 2 hydrogen. The other 2 here are what? Are electrons. So if you took those 2 electrons off, the derived geometry of water is what? Is bent again. Okay, is bent again. Of course, the bond angle is 109.5. Again, the derived 1.4 is, we assume is 109.5. We don't talk about in this class why there are 104.5. Okay, you assume is, if it is tetrahedral, the geometry is 109.5. So this is what water molecule looks like. A bent. Because there's a lone pair here, there's a lone pair here, but there are lone pairs. So this bent is derived from what? From tetrahedral. Okay, derived from tetrahedral. So in summary, for 4 electron groups, the geometry of the groups is tetrahedral. And the bond angle is 109.5. That's all. We all assume they're 109.5. But you need to look at the lone pairs. If the molecule has 0 lone pairs, then the geometry of the molecule will be what? Will be tetrahedral as well. If there's a 1 lone pair out of those 4, if there is 1 lone pair, the geometry of the molecule will be what? Will be a derived shape called trachinopyramidal. Okay, trachinopyramidal. Yeah. If there are 2 electron groups, the geometry of the molecule will be derived called bent. Sometimes we call it angular. Okay, angular shape. Bent and angular, same. And the bond angle again is what? 109.5, because these shapes are derived from what? From tetrahedral. And you need to look at how many lone pairs. Okay, how many lone pairs. So here is a summary of what we have learned regarding how do we tell the geometry of a molecule. What are the steps you need to do? First step, again, is to draw a correct Lewis structure and identify which atom is the central atom. That's the step 1. Step 2 is use the VSEPR, this part theory, to determine what? Determine the number of electron groups. Okay, when you determine number of electron groups, pay attention to 2 things. One is we don't discriminate bonding or non-bonding electrons. And we don't discriminate single, double, or triple bond. They're all counted as one group. Double bond, 4 electrons, one group. Triple bond, 6 electrons, one group. We don't discriminate this type of bond when we don't discriminate bonding versus non-bonding. Bonding, one group. Non-bonding, one group as well. And finally, use the theory to determine the geometry, because these groups will minimize the repulsions by what? By separating the maximum. 2 groups, linear. 3 groups, trigonal pyramidal. And 4 groups, tetrahedral. And finally, when you determine the geometry of the groups, you need to consider lone pair or non-bonding electrons as well. Because if you have non-bonding electrons, the molecule geometry will be a derived geometry by taking away the non-bonding. Okay, taking away the non-bonding. Here is some examples. Okay, here's a link showing molecular geometries. You can play with it. Okay, 2 groups without lone pair, linear. 2 groups, 4 groups with 2 lone pair, bent. This one, 3 groups with 0 lone pair, trigonal planar. This one, 4 groups with 1 lone pair, trigonal pyramidal. 4 groups with 0 lone pair, tetrahedral. Okay, these are examples. Again, further, I hope further you understanding about the geometry of the molecule. Okay, further understand geometry of molecule. And here are some practice. Okay, some practice. And I gave you the Lewis structure here already. So hopefully you can draw the Lewis structure first and then determine the geometry. Okay, I'm going to quickly go over the geometry. The first one is tetrahedral geometry because 4 groups. The second one is also tetrahedral geometry, 4 groups. The third one is 4 groups, but with 2 lone pairs. So derived shape called what? Again, 4 groups. We have 4 groups, 2 bond, 2 lone pair. But we have 2 lone pair, mean the geometry of this SO2, H2S is bent. Okay, it's bent. Here are more practice for you. Okay, I'll leave it here. And again, the key is provided. I hope you to practice using the theory and step by step and show me how you determine the geometry. But first of all, Lewis structures. Okay, Lewis structures. After that, let's take a look. Why carbon dioxide and molecule like carbon dioxide and water, they can absorb IR. This picture shows kind of like a summary of how different radiations will cause different behavior of a molecule. Okay, we learned that UV in chapter 2, UV because it has higher energy than visible light. The energy is relatively higher. It will cause the molecule to break a bond or dislodge electrons out of a molecule to cause charged species. But infrared, on the other hand, okay, infrared on the other hand, don't contain enough energy to cause any bond to break. Okay, to cause a bond to break. So what infrared actually does is cause bond to rotate. I'm sorry, cause bond to vibrate. Okay, because it doesn't cause bond to break because it's not energy now, but it does cause molecule to what? To vibrate. Okay, to vibrate. Vibrate means what? Means the bond can stretch, can bend because vibration. And finally, before we can just very briefly, microwave. The energy is even lower because the wavelength is even longer. Normally cause small molecules like water to rotate. Okay, to rotate. And that rotation like water will cause friction. So that temperature of the water will increase. That's the principle of how we use microwave to heat our food. Because microwave cause small molecules, especially water in our food, to spin fast, spinning rotation. And that spinning causes friction because molecules are friction, interact with another molecule. And that friction causes the temperature of the water to rise so that you can heat your food. So that's microwave, cause molecules to eat, cannot even cause vibration. Okay, again, back to our IR. IR don't have enough energy to cause chemical bond to break, so IR cause bond to vibrate, to stretch, and to bend. Okay, and to bend. So here, let's take a look. What vibrations do we have for carbon dioxide, for the greenhouse gas carbon dioxide? If you assume the carbon and 2 oxygens are 3 bonds, and these 3 atoms are linked by bonds, and we assume the bonds are springs, it will be easier to understand what vibration means. Okay, vibration means when a molecule is radiated by IR. We know IR is a spectrum, is a range, right? From 1 nanometer to nanometer is a range. But when a certain wavelength of IR, or when a certain frequency of IR matches the vibrational energy of the molecule, then that particular IR will be absorbed by the bond to cause the molecule to vibrate. Okay, cause the molecule to vibrate. Again, IR is a range. When a certain vibrational energy of the IR matches the vibrational energy of the molecule, then that IR will be absorbed, will be taken away. What's that used for? Used for cause the molecule to vibrate. So this means different molecule, because they have different geometry, they have different bonds or different bond and vibration energy. So different molecules will absorb IR radiation at different wavelengths, and that's therefore vibrate at different energies. Okay, vibrate energies. For carbon dioxide, there are 4 types of vibrations. If you pull the string equally on both sides, we call that stretching and symmetrical stretching, because you're pulling on both sides. If you squeeze one string and stretch another string, we call that asymmetrical stretch. Again, you're stretching. Again, pull on both sides, we call that symmetrical stretch. If you squeeze on one spring and pull another spring, we call asymmetrical stretch. This is asymmetrical, that's symmetrical. And of course, if you don't stretch, if you cause like molecule to do like this, we call that bend stretching. Okay, we call that bend stretching. So that means not along the axis of the string, but doing like this. We call that bending vibration. So for carbon dioxide, there are two main big types of vibration. Stretching vibration, okay, stretching vibration, and bending vibration. Okay, and bending vibration. Now, from this picture, you can see what IR absorption really means. IR absorption can be demonstrated with IR spectrum. So you can see that when you radiate the molecule with IR, with full strength of IR, but when a certain wavelength of IR is absorbed, the IR line is gonna drop. So you're gonna collect upside down peaks. And this upside down peaks here and peaks here shows you what? Shows you this part of the IR are absorbed by carbon dioxide. The rest part, these are not absorbed. They're still full strengths of IR. Only when IR strength intensity goes down means what? The IR, this part of IR is absorbed by the molecule. That's why we said the vibrational energy of the molecule must match the energy of the IR to be absorbed. So for a long spectrum IR, only a certain part of IR will be absorbed, and those sorting part of IR must match the vibrational energy. So that means for carbon dioxide, this is the part of IR being absorbed, and that's the another part of IR being absorbed. And mainly for carbon dioxide, we have two groups of absorption. The one around 4.3 micrometer wavelength absorption corresponds to stretching vibration, because stretching takes higher energy. So you need shorter wavelength IR to cause the stretching. So this group B is stretching vibration, while this group C and D with the wavelengths around 16 micrometer is bending, because bending takes less energy. It's easier to bend than stretch. Okay, so bending is easier. So you doesn't need that higher energy IR. Lower energy IR to cause bending vibration. Lower energy means what? Longer wavelengths. So the longer wavelength one corresponds to bending vibration, and the shorter wavelength one corresponds to stretching vibration. Now, for these 4 types of vibration for carbon dioxide, only B, C, and D cause IR absorption. Vibration A, which is what? Pulling on both sides, called symmetrical stretching, does not cause IR absorption because it's symmetrical. So the overall dipole of the molecule, the charge distribution of the molecule, does not change during vibration. And even though there's a stretching, these 2 charge distribution cancel each other because the geometry is linear. So in symmetrical geometry, stretching vibration, these 2 charge changes causing the vibrational energy cancel each other. So symmetrical stretching is not showing in IR spectrum because it does not absorb IR. The IR absorbing vibrations are asymmetrical stretching and what? And bending. Okay, and bending. So that's what IR spectrum looked like. If you put a high carbon dioxide molecule sample, you will see that there are 2 groups of absorption. Okay, absorption. Now, any molecules of 3 or more atoms can absorb IR and can be an infrared gas. Water, of course, is more important than carbon dioxide as a greenhouse gas because water also has 3 atoms. You can see that water has symmetrical stretch, asymmetrical stretch, and bending stretch. But because water is bent, okay, this is what water moves like. So even symmetrical stretch of water will cause vibration because water is not linear. Okay, linear, you can cancel each other. Bent water molecule cannot cancel each other with the symmetrical stretch. So the 2 groups of water, okay, 2 groups of water, absorption, IR absorption, corresponding to stretch and bending, the same. Okay, the same here. With shorter wavelengths corresponds to what? Stretching. Longer wavelengths corresponds to bending. Okay, here's a practice showing you. Okay, asking you, can you explain which part of the wavelengths correspond to which type of absorption? Okay, remember, stretching takes higher energy. So stretching vibration wavelengths will be shorter. Bending will be longer. Okay, and finally, we said only molecules with 3 atoms or more can cause IR absorption. Diatomic molecules, such as the main component of the air, nitrogen or oxygen, they do not contribute to any IR absorption. They're not counted as greenhouse. The reason is very simple. Just like symmetrical stretching of CO2, the overall electric charge distribution does not change during bond vibration because they're symmetrical. Okay, no matter you squeeze them or pull them like these demonstrations, the overall charge distribution during vibration don't change. And if they don't change, they are not actually IR absorbing. So diatomic molecules like nitrogen and oxygen do not absorb IR because the electric charge distribution does not change. So their vibration is very similar to the vibration of carbon dioxide, symmetrical stretching, which does not contribute to IR absorption. Okay, so that's the first part of this chapter. Okay, we're going to stop here. I'll record the second half later time. But in this part, we mainly discussed the main idea of chapter 3. That is, what is the term of global climate change. Okay. What is the potential cause of global climate change? And when we talk about climate change, we have to understand we need some of the greenhouses to keep us warm, and why they keep us warm. And we also studied, in order to study why they keep absorbing IR radiations, we need to study the geometry of them, okay, by using this theory called the whisper model theory. Once we know the geometry of the molecule, we can determine whether they absorb IR or not. Okay, so these are the topics we studied, okay, about chapter 3, the first part. The second part of the chapter 3, we're going to discuss, okay, remember we talked about the carbons, the carbon cycle. We put more carbon in, we put the carbon out. We're going to talk about some calculations about chemistry, about how do we quantify substances, matters. Of course, how do we quantify carbon is the topic around it, but we're going to learn in general, in chemistry, how do we quantify matters, the calculations in chemistry. So stay tuned for part 2. Bye now.